फोटो कटवा देना स्क्रीन से क्रॉस नहीं टॉपिक चला लेना yes so it's good evening everyone present over here. So it's sharp 5 o'clock and I guess it's a perfect time to start our session. So my name is Sanjay and today we will be taking a seminar on practical applications of FEA theory. So let's start for the session. So like as we are engineers, our main aim is to make the life easy by finding the various techniques, various methods. So while making the life easy, we face different problems and that we solve it to get a solution. So while getting the solution over it, it goes through the various process. So how to solve that? First, we need to define a problem. What is the need? What is the need? For what we are doing exactly. Then we need to gather the information regarding it. Means what are the inputs required for it? What is its use? What are the other options for that? And these all things we need to gather the information. And based on that, we need to generate multiple solutions because any single problem will have the multiple solutions. So we need to see all the possible ways to solve the problem. And then we need to go which one is best among that. There will be so many solutions and which is feasible or which is more economic or which satisfies our need better. So based on that, we can have a best solution over it and then solve that solution. When you get the proper result, then that we can interpret, with the test and that all. And then if it satisfies our defined problem, then we can have that the solution is perfect. So like this, the engineering process goes. So when it goes through the engineering process, the same problem can be solved by the 3 methods. So either it can be experimental method, so it can be analytical method, or it can be the numerical based approach. So experimental method we can apply only for the smaller geometry and that all. Suppose if we have aeroplane or something, if we have to do the crash analysis of it, directly we cannot crash the aeroplane, right? So because aeroplane is costlier and doing experiment on it is not feasible. So that is the limitation of experimental approach. So one more comes, it is analytical approach. Analytical approach is nothing but where we solve the problem by different formulas. Like stress, if we want to calculate, we can calculate it by force by area, but provided that the area should be definite. Means we should have the proper measurement of that area. Like we can calculate the area of the stool or rectangle like that, and applied force divided by that area, we can get the solution. But this analytical approach cannot be applied for the complex geometry. As for the complex geometry, we cannot find the area and that all. So that is the limitation of the analytical approach. So over this, there is one more term called numerical based approach. So for the numerical based approach, we are using the finite element theory. Finite element theory, where the problem means it is discrete. CAD is converted into finite elements, and on that finite elements, boundary conditions are applied, and these are solved. So the main motto or main objectives of our today's presentation is that our theoretical based approach, how they are used in generating the best solution in a practical way. So let's go further. Yes. So these problems, FEA based problems, are like various problems are there. In that we are going to see the mostly on the structural problem. So the structural problems are classified based on three types. That is material linearity, material non-linearity. The second one is geometrical linearity, geometrical non-linearity, and third comes contact linearity and contact non-linearity. So let's go like what exactly I mean linearity. First, we will go for the the material linearity. So where we can see that what it says that force displacement relation is linear. It means like when you apply the force, the displacement is linear in nature. I mean it follows the equation of straight line. This red line we can see it is linear. It is like following the equation like y is equal to mx, and this blue color shows it is non-linear nature. Suppose if we take one example, like here we can see the universal testing machine where the tensile test is being carried out. So for the test specimen, we are applying the gradual tensile load. So as you are increasing the load, the displacement is increasing. So the load versus displacement is calculated in terms of stress versus strain. So stress versus strain is linear up to Hooke's elastic limit, which is known as Hooke's law. So here it is linear in nature. So this kind of study we can call it as material linearity. So going further, so non-linearity, what it means exactly. So now we can see the curve here. Now the curve is not like tracing the equation y is equal to mx. It is not the straight line. In the second figure here we can see here up to the like shaded region, the stress strain curve is linear in nature. It means elastic in nature. So these problems can be solved by considering it as material linearity. To solve this problem, only we need to have Young's modulus, density, and Poisson's ratio. So again, if you want to go for the like a plastic region, I mean, if you want to study how the material is behaving in its plastic properties, so we need to have the plastic properties. So here Young's modulus cannot be constant because Young's modulus is stress upon strain. It is slope. So Young's modulus cannot be constant over here. So we need to give the stress versus strain values to the software so that it can calculate the non-linearity in nature. Okay. So next type comes, it is like geometrical non-linearity. So the best example it is considered here, it has buckling. So buckling, I mean, here in the first session, like a first type material non-linearity, we said that it is, I mean, linear below the elastic limit and non-linear after the plastic. So linear means elastic limit means the deformation will be very small over there. So next comes geometrical non-linearity. Here this also like applied for the like large deformation. Suppose if we are applying the compressive stresses on a column, so initially if the column length is too high, initially the column may not bend, but upon higher loading, the column will bend and this will buckling will occur. So where the deformation will be more, and this kind of large deformation like can be analyzed from the geometrical non-linearity, because when we deal with FEA, everything relates with a stiffness matrix. So stress, strain, or stiffness matrix. So we will be having the equation like F is equal to Kx for static, stiffness matrix, force input will be there. From that displacement will be calculated. So when we apply the load in terms of increments, I'm repeating again, when we apply the load in terms of increment, suppose if you want to apply 10 kilonewton load, all 10 kilonewton load I cannot apply at a time. So initially the 1 kilonewton load is applied, then the system is checked whether it's in equilibrium or no, whether it is stable or no. If it is stable, then the next increment in load is applied. So similarly, so for the next iteration, we need to have the updated stiffness matrix. We cannot have the same stiffness matrix because because for the large deformation, stiffness matrix changes as the deformation increases, because the stiffness totally depends upon the area and the length as well as the Young's modulus. So deformation is increasing, it means that the stiffness matrix is getting changed, and because of that, I mean, the updated stiffness matrix has to be considered similarly how we consider in like calculating the true stress or true strain back compared to the engineering stress and engineering strain. So update after taking the updated stiffness matrix, we can get the geometrical nonlinearity can be considered into the picture, and which gives the more like accurate result compared to the geometrical linear problem. Yeah. So yes. So before, and one more comes, it is like a contact nonlinearity. So where the contact nonlinearity, it means where if you want to solve the problem with a beam, so we can form the rigid into that, and yeah, the force will transfer to the rigid element. So but when there is, like, if we take the example of gear or something rack and pinion, so there may not be the node to node connectivity, and because of that we need to give the contact elements over there, and the contact nonlinearity can be solved. Yes. So now going further, so all the problems, static problems, can be solved by the can be solved by the equation like mx double dot plus cx dot plus kx is equal to f of t. So I mean all the structural problems. So where one more thing I would like to make it more clear, any product or any component in the universe can be represented in the form of spring mass damper system, any structural component. So it will have its own mass, it will have its damping capacity, I mean to absorb the vibration, and it has something like K spring property, I mean it has some stiffness. So when we apply the force of it, the three kinds of terms will generate. So mx double dot plus cx dot plus kx is equal to f of t. So applied force is a function of time. So that is nothing but f of t, applied force vector. So x of t, it is nothing but displacement. X dot t, it is velocity, and x double dot t is nothing but acceleration. So similarly, we have k, it is nothing but stiffness. Stiffness, it defines the stiffness. So it is force per unit length or force per unit displacement. So damping is force per unit velocity, and we have mass like that. We can say it as from the Newton's second law, it will be F is equal to ma, because x double dot is acceleration. So F is equal to ma. So that is called it as inertia force. So inertia force, viscous force or damping force, and next term comes is as stiffness. So based on these equations only, all engineering problems are classified. So yes, going further, the analysis are classified again in terms of static analysis and the dynamic analysis. So in the static analysis, the force and displacement remains constant with respect to time. So in the previous slide we saw, in the static analysis, there will not be time because load will not change with respect to time. The cx dot and mx dot terms will get cancelled out, and only we will be remaining with the term f of f is equal to kx. So that is nothing but static load. So force is applied, just force is applied, and it will have stiffness. So f is equal to kx equation. So here if we see the chair is being analyzed, suppose now I'm sitting on the chair. So chair is carrying my load, my weight is around 65 kg. So 65 kg into 9.81 Newton, that much load will be applied on the area, how much my body is coming in contact with the chair. So on that much area the load is applied, and the stress is calculated. Stress and the deformation is calculated over here. So we have taken a small engineering problem over here. So where the small bracket is there, and upon that it is fixed at some end, and the force is applied in the x direction. So when we apply the force in x direction, that is almost about 3,300 Newton force. So after applying that, we are plotting here the displacement as the stresses. So we can see over here displacement plot and the stress plot here. So what are the limiting values for it now? So here for the displacement, there will not be limiting value. Limiting value will be equal to based on the other part which is coming in contact with this part. And for the stress, there will be the limit 250, or yield stress will be the limit. So for this, yield stress is 250 for this material what I have given. So above the 250, whatever it is coming, it is failing in nature. So for the static case, the force and moment has to be in the balance in nature. So the applied force is should be equal to the reaction forces. So here we have calculated the reaction force. So sum of applied force, it is nothing but 3,300 Newton in X, and same reaction force is generated. I mean the reaction forces which are same in magnitude but opposite in nature. Here we can see like X force. In a Y, the applied force is almost zero. So the generated force is equal to the 10 raised to minus 7, which is almost equal to 0. So Z also, force and moment are almost equal to 0. So moment about X is 0, but we have got the moment about Y and moment about Z. So the moment about Y, it is applied moment, and the same moment in reverse direction it is generated, and same with the Z. So this is like a static problem where the force is not changing with respect to time. So next comes it is dynamic problem. So as I saw in the first case, so dynamic case means force is varying with respect to time, and it will have the the velocity and the acceleration terms also will be there. So the damping force and inertia force has to be considered, and this kind of problems, dynamic problem, can be solved this dynamic problem is used in the crash analysis and the modal analysis and that all. So the upcoming examples will be more clear. So these problems can be solved by the CAE methods. So in the CAE methods, so basically there are it is solved in the 3 steps. So modeling, then a solution, and then the post processing. So here we can see the model, right side diagram. We can see first the model is taken, model is meshed into the Hypermesh or any meshing software like ANSA or ANSYS. And for that, the material properties, load, constraints are applied, and then it is solved in the solver solution. So there are different solvers like OptiStruct, Abacus, Nastran, LS Dyna, ANSYS. So based on the problem statement and based on the type of problem, it is taken into the various software which is more convenient to solve the problem. And then the post processing is done. So post processing also there will be different softwares. So it is analyzed into the different softwares. So going further, now exactly how our theoretical concepts are used in the our FEA method, that we are going to see. So here a static analysis we are doing on a simple beam. So here the beam, we can say it is a cantilever in nature. So on which free end we are applying force and has the length L and the width and the height. So here goes the problem statement. So problem 1. So the static analysis of a cantilever beam having circular and square cross section, and take Young's modulus is equal to 210 gigapascal. So only we are solving for the square cross section. So here 1000 mm is the length and force is applied. So force is nothing but P in this formula we can see, and 20 into 20 is the cross section. So suppose if you want to calculate the deflection, the deflection can be calculated by the equation PL cube divided by 3EI. So we have L, where L is equal to 1000 mm. So P is nothing but force, applied force, that is equal to 10 kilonewton. We have the 3 is the constant. E, we have here the Young's modulus is equal to 210 gigapascal. And I is nothing but moment of inertia, and moment of inertia can be calculated from the cross section. That is based on breadth and height, or breadth and depth we can say. For the square cross section, it is BD cube by 12. So based upon that, we can get the inertia, and this is the formula to calculate the deflection for the cantilever beam. Delta is equal to PL cube divided by 3EI. When we solve this problem by the analytical method, we got the answer is equal to 0.01864. And when we solve it exactly in the simulation, we solve in the software. So in the software also we can see the answer. We have got it as 1.8 like 18 into 10 raised to 1. I mean it is 18.68 mm. So if we convert it to the meter, we will get it as 0.01868 meter. So what we can conclude from this static analysis? So when we are able to define the exact physics or exact problem statement to the software will give the correct answer, correct values. Because if we give any input, the software will give output, but provided that the input given by us should be more clear. So this that much great accuracy can be solved, can be we can get it from the software, software or FEA approach what we are using it. So next we will go for the modal analysis. So modal analysis, yeah. So modal analysis is carried out to check the natural frequency and the mode shape of the system. So I will go for the previous slide. So here mx double dot plus cx double dot plus kx is equal to f, it is there. So in the modal analysis, it is called it as free analysis. Means the external applied force will be equal to 0 and the effect of damping is not considered. So the equation reduces as the mx double dot plus kx is equal to 0, and that equation it is well solved. You all may be knowing it very well. You have studied in your engineering days. So mx double dot plus kx is equal to 0. So x is so it is satisfied for the sinusoidal wave. So it is like a sine omega t, and if we solve it, we will get the natural frequencies like omega n is equal to root of k by m. So question arises, why the natural frequencies are to be calculated and what the mode shape exactly says. So natural frequency of the system is calculated just to know the resonance effect, because if the natural frequency of the system matches with the surrounding component's natural frequency, it will lead to the maximum vibration, and the phenomena is called it as resonance, and it results into the failure of the component. So when we solve the exactly modal analysis, so we get the eigenvalues which talks about the natural frequencies and eigenvectors which talks about the mode shapes. So mode shape is mode of vibration, how it is vibrating. So let us go for the next slide, so where the picture will be more clear. So this is yeah. So this is the component CAD. We have meshed it in the FEA. So meshed view looks like this. Sorry. And then we need to give the eigenvalues to calculate it. So eigenvalues, the number of eigenvalues, we have option called it as V1 to V2. If we know the frequency range, then we can give the frequency range ranging from V1 to V2. And if we don't know the frequency range, then we can give the number of modes, how many we want. So the EIGRL card, this only card is enough to calculate the or mode shapes or natural frequencies. So here we have, the option called normalization, where we have max normalization and max normalization. It doesn't make much difference into the analysis, but based on max normalization and max normalization, the solution, the post processing becomes easy, and it becomes easy to interpret the result. So when we solve it in the software, we get it the answer like this. So I have solved it here by both the methods, by the max normalization as well as the max normalization. So here we can see the eigenvalues, and here we can see the frequencies. So once if we have the close view, so eigenvalues is nothing but we have got the terms like omega n. So omega n is nothing but the eigenvalues. So for this eigenvalues, and omega n is equal to, we know it is a 2 pi fn. So for this omega n value, eigenvalue, first eigenvalue, if I divide it by 2 pi, I will get the frequency. That is nothing but fn. So in both the cases, we can see the obtained eigenvalues and the obtained frequencies, it is same. So because omega n is nothing but k by m. So but here we can see that the generalized stiffness and generalized mass is changing in both the ways, mass normalization and max normalization. In the mass normalization, it will try to take the mass, it will try to do the mass, it is equal to 1 mass. It is nothing, it is not only the mass, but it is modal mass, because we solve it omega n is equal to k by m, but k we will be having the stiffness matrix, and even m too we will be having the mass matrix. So stiffness matrix divided by the mass matrix, when we do it, we will get it as the frequency. So this is the generalized mass and not only the mass, and this is the generalized stiffness. So k, generalized stiffness, it is calculated by phi transpose k into phi. So phi is nothing but the eigenvectors. And in the next case, we can see that the generalized stiffness is changing and the generalized mass. So where the max normalization, in the max normalization, the maximum obtained eigenvector is taken it as 1. That the maximum displacement will be considered as 1, and all the displacements are calculated in terms of that. So going further, this approach, this numbers will be more clear when we see the practically the result interpretation. Now, yes. Now we have, so before that, so if you see here the first 6 modes, so first 6 modes are like almost is equal to 0. The frequency we are getting it as 0 because this is free analysis. So in the first 6 modes, the body will try to constrain itself, and upon constraining, then only it will give the next deformation, and that all. So this is like thing but 6 modes, and directly after 7th mode onwards, we will be getting the frequency almost is equal to 123.82 hertz. That is first natural frequency we can see. And if you see now, I have plotted the mode 1. So for the mode 1, if we see by both the method, mass normalization as well as the max normalization, we can see. So in the max normalization, in the displacement here bottom at the node 1, it is almost is equal to 1.007, or it can be like maximum displacement, it is 1.01 is in nature, which is equal to 1.007. And here the counter plot in the first image is also the same as the second image only, but here we are getting the displacement is equal to 63.401. Why it's so much big difference? Because the displacement what we are getting, those are not the absolute values, but those are relative values. But the frequency what we are getting, that is absolute value. So just the displacements are relative in nature and not the absolute in nature. So the plot goes like this, and here we can see that the body is not deforming. If we see the animation, the body, it is displacing and not deforming. So if I go to the next slide also, now here we can see the mode 4. So mode 4 is nothing but rotation about the x-axis. The body is trying to rotate about the x-axis. So when it is rotating about the x-axis, it is not deforming again. So but it is displacing. So yeah. So when it is deforming, the strain energy will induce into the system. So based upon strain energy, like we can calculate the we can improve the natural frequency based upon the strain energy. So now if I see the seventh mode, so 7th mode, it is after the 6th mode. 6 modes are the rigid body modes, and the 7th mode we are getting the the deformation. So the deformation, it is like this. So the body is changing its shape. In the first 2 modes, body was not changing its shape, but it was changing its position. Now here the body is like at the same place, but deforming. It is deforming in nature, and because of such deformation, the strain energy will induce into the system, and this is like the strain energy. Strain energy is calculated based upon the displacement, because based upon the displacement we will get the strain, and based upon the strain we will get the strain energy. And as previously I said, The displacement itself is not a absolute value, it is relative value. So the strain energy will also be equal to it will be also relative in nature. So here what red maximum area we are seeing, so this is comparatively the weaker region. So weaker region in nature. So where the more strain energy means the body is deforming more. So there will be the less stiffness, less stiff the body. So in this region, we can improve the stiffness. So the stiffness can be improved by the various methods. So we can add the ribs for the plastic components. We can increase the thickness. We can add the beads to the system for the BRW components and that all. And the stiffness and in which direction we need to apply. So in which, like it is like oscillating or opposite to the mode shape, we need to add the stiffness. So if we add the stiffness, so the natural frequency of the system can be improved. So this was like more about the modal analysis. So the CAE, like what we are using, it has the various applications. So here the design decisions can be made like based on the impact performance and that all in the crash analysis. So like it can, like in the risk criteria, I mean, will be less. I mean, we can manage the risk and understand the performance of the design, what we are doing it actually. And designs can be evaluated and refined using computer simulations rather than physical prototype testing, saving time and money. Because when we build the model of the car or something, it goes through the various like iterations. So upon every new iteration upon every small change in the design, we cannot manufacture it and we cannot go for the practical testing. So we need to have the simulation in the software itself, so where we define the exact physics and we get the exact results in the system. So this is like nothing but the impact loading and that all. So like where the impact loading, I mean how the analysis is being carried out. So here the different like car FEA model is there. So in the car FEA model, like I have trimmed some of the components so that we can see entire things. So there will be the different like so see there are, first let us go for the bottom. So this is the actual crash carried and this is the in the software crash carried in the software. So in the both way we can, in the both the images or in the both the GIF, we can see that the results are almost matching. The theoretical calculation is resembling the practical the loading condition or the experimental loading condition. So to get this, we need to define the exact the physics for the problem. So this is the example of the rear impact and this is the example of the frontal impact. So where initially first we will be having the mesh. So for this mesh, we need to define the material, different linear material, non-linear materials, we need to define it. And we need, in the tires, we need to define the tire pressure, how much we want. So, and all the components are connected by the various connections, like rigid connections, spot weld, seam weld, bolt connection, adhesive connection. There will be the connection in between the two parts, like by taking the bush, spring, dampers. So such all loading conditions we need to apply for the system. And then the connections, and we should define the kinematics of the system very well. So to define the kinematics, we need to give the joints, so that there will be the different kinds of joints like spherical joint, revolute joint, universal joint, and that all. So here we can see in the tires we have defined the revolute joint. So the tires will rotate about this. So after giving the exact material properties, mass is checked, properties are checked, everything, the loading condition is applied and it is made to strike it over here. And also we need to define the FE properties. So when we defined it exact physics, so practically we will get this condition. And here like how the energies are transferred and that all, so that can be seen over here. So going for the next slide. Yeah, so it is the continuation of the first slide only. So upon the impact, right? So the vehicle will have the kinetic energy. Vehicle is traveling with certain velocity. So it will be having the mass as well as the velocity. So the mass into velocity, like mass into velocity square, half mv square, we will be having the kinetic energy. And the results for this, it is plotted over here. So the total energy in the system is constant in nature. Constant in nature. And upon like impact, the vehicle is decelerating. So vehicle is decelerating. So the velocity is decreasing. So there will be the drop in the kinetic energy. So we can see here a blue line where the kinetic energy is decreasing parabolically in nature. Yeah, energy should be the same throughout. So it has to be compensated. So it because when it deforming, it is absorbing some kind of energy, that is strain energy, or we can call it as internal energy. So internal energy will keep on like increasing, because it is like deformation is occurring, and when it is deforming, is storing some kind of energy. So the internal energy will increase, kinetic energy will decrease. So there will be two more energies we can see here, like bottom, a red color line and one green color line. So those are nothing but sliding energy and the hourglass energy. So the sliding energy occurs mainly because of the frictional values. Friction we are defining, contacts we are defining between the various components. So because of that, the the sliding energy is increasing, and the hourglass energy is also increasing little bit. That is because of the less accuracy in defining the problem, or less accuracy in defining the mathematics, or less accuracy in defining the behavior of the particular element. So because of that, we can get the hourglass energy. But these two energies are well below the like 5% of its limit, and that all. So that is not a much big problem. So based upon this, at what time which component is absorbing how much energy, and that all. So that can be like analyzed from this graph, and that all. So this is for the dynamic. So there is like it is solved by the explicit dynamic code. So there is one more picture over here. We can see the seat is there. So on the seat there is like seat belt like blocks are being placed. So there is shoulder block and there is lap block, which exactly resembles the human body. The shoulder block is kept at certain angle. So there will be the 3 points. The here there will be the buckle point. So here there will be the D ring, and there some floor anchorage point will be there, and H point will be there. So H point, the dummy will have the H point in the near the hip region. But H point has to be matched or coincident with the reference seat reference point. And for this, belt routing is done. So belt, it is routed from the buckle to the shoulder block, and from the shoulder block to the D ring. So D ring means from the where the slipping of the belt can occur. And here to the lap block also we are doing the belt routing, and for this we are applying the load. So load is the thing, but it isn't quasi-static in nature. So for the particular this analysis, seat belt anchorage analysis, so the load applied is almost like equal to the 13,500 Newton load is applied over the 280 milliseconds or 0.28 seconds we can see. So after applying the load, what are the changes occurring in the things? So how the seat is behaving, which components in the seat are failing, and which components in the D-ring, retractor, floor anchorage are failing, that we can see in the this simulation. So here there will not be the kinetic energy because it is quasi-static process. The increment in load is almost negligible. So there is very small increment in load, and because of that the velocity term will not be come into the picture. I mean the part will not have inertia, and because of that, I mean the kinetic energy induced is very less, so that is almost equal to, should be equal to 0, and total energy should keep on increasing, and that is like the internal energy should also trace the same path over the like kinetic energy. So yeah, that's it. Like this the quasi-static analysis can be like analyzed so by plotting the energy versus time curve. Similarly, this like analysis what we carried, it was just to evaluate the structural performance of the vehicle. Also the occupant safety can be solved by the solver called LS Dyna. So where upon accident the airbags are deployed, and the I mean airbags gets activate, and then we will see how much time it has taken to activate the system. I mean how much time it has taken to activate the airbag, and various factors are calculated like head injury criteria, traumatic uh, th- traumatic thorax index, that it is calculated, and I mean the then for the chest injuries are calculated, and how much force it is coming on the like our legs, that is being calculated, and based upon that the safety of the dummy is calculated. The same approach can be used for the householding devices, I mean the drop test and packaging. So like the systems like washing machine, water filter, or fridge, or TV, such kind of things are analyzed for the drop test, because while going for the manufacturing process is, or like while delivering it from the like from the like manufacturer to the customer, it will go from the various people or various things, it is supplied managers. So while handling it may drop, and that all. So the drop analysis of the drop tests also it can be like calculated by using the LS Dyna. So these are the things, and based upon that, like how much energy it is absorbing, how safe the inside components are, that can be like well solved from this kind of like example. So like finally I would like to conclude my paper, or like my presentation, like by saying that the FEA methods gives the exact results as the experimental load, experimental like tests, or the like the analytical tests what we are doing. So when we give the exact physics, it gives the exact results, and all kind of problems, though it may be the NVH, or it may be the crash, or it may be the like durability or the fatigue analysis, can be solved by the various software like Abacus, Nastran, Dyna. That's it, provided we give the exact physics to it. So like finally I would like to conclude by saying that like the practical like the theoretical concepts what we are studying it, if we apply it proper in a proper way, so the more exact picture we can get it. So that's it from my end. Like thank you for attending us today's seminar. Thank you one and all.